So this is the third video out of 4 for the precise definition of a limit. Now, in the first video, we talked about two-sided limits. In the second video, we talked about one-sided limits. And in this video, we are going to describe limits at infinity. Okay, so before I do that, we're going to recall the information about two-sided limits. So the limit is f of x, our function, is defined on an open interval around n. We say that the limit of f of x as x approaches n is the number L, and we use this notation. If for every epsilon greater than 0, every small positive distance, there exists a corresponding number, delta, also a small positive distance, such that if x minus n is between 0 and delta, this implies that f of x minus L is less than epsilon. Now, again, this is just trying to describe how close we need to be to n to get answers close to L. Okay? Now, the question becomes, how does the definition change for limits at infinity? It's not going to be the same as a two-sided limit because limits at infinity don't have two sides. Okay? In order to do this, I'm going to introduce two new symbols. The first is m and the second is n. They are used pretty interchangeably. It's not like one of them means one and the other means something different. They're pretty much just, we use whichever one we feel like using. They're both used to represent large numbers. Now, I'll mention sometimes people will use m to represent a positive number and n to represent a negative number, but that's not required. They are interchangeable. So let's talk about the limit at positive infinity first. So let f of x be defined on an open interval m to infinity. So we want to include, at a minimum, or at least be close to m. We say that the limit of f of x as x approaches positive infinity is the number L, written using this notation, if for every epsilon greater than 0, there exists some corresponding number m, again, m is a big number, such that any x values greater than m put me close to L, put me within epsilon of L, okay? So, again, we're going to approach this visually, but notice again, we're changing up this first part, but since the second part is a number, I'm going to leave that alone, okay? Now, here's what it looks like visually. So there's L, and we have L plus epsilon and L minus epsilon as my boundary. Now, what I'm going to try to do is try to find some number m as essentially a cutoff point where everything beyond m, everything to the right of it, is in between these boundaries of L plus epsilon and L minus epsilon. Now, if you'll notice, I could actually move m back to the left a little bit because even over here on the a little bit on the left, it's still within that boundary. But again, m is just a cutoff. It's anything past it should be close to L. Okay. Now, similarly, if I do the limit at negative infinity, I want to choose some number that is less than n. I want to choose some big negative number, okay? So let f of x be defined on an open interval from negative infinity to n. We say that the limit of f of x as x approaches negative infinity is the number L with this notation. If for every epsilon greater than 0, there exists a corresponding number n less than 0, that's how I'm defining it as negative, such that for x less than n, for x being beyond that negative number, implies that f of x is close to L within epsilon, okay? Now again, we're just going to look at another function. So here's my blue function. My L in this case looks like it's 0 because that's my x-axis. So we're going to go a little bit above with L plus epsilon and a little bit below with L minus epsilon. And n is my cutoff. Anything to the left of n should be in between these two boundaries, L plus epsilon and L minus epsilon, in this blue shaded region. All right. Now, I'm going to go over a couple of more things before I move on. So I want you to think about this, and this is very important. Since x is approaching infinity, whether it's positive or negative, you should think about m or n as a cutoff point. Everything beyond m or n is really close to the limit's answer. We want it to be really close, okay? Now, furthermore, I'm going to recap. All limit at infinity definitions start the same way. Pay attention to the variables m and n because, again, they can be used interchangeably. It doesn't really matter if m is positive or if n is negative. N is just a symbol. M is just a symbol. We can use whichever one we want. After a certain number, Everything else should be within that appropriate range of values. Again, going back to this picture, after n, if I go left of it, everything should be in this boundary in between these two dotted horizontal lines, okay? Now, notice, depending on what our x approaches, alters just the first part of the definition. I'm going to categorize these kind of broadly, and that's why I separated them into videos. The two-sided limit starts with something like this, or one of those alternative versions that I've given earlier, video 2. One-sided limits will either, depending on whether you're left or right, will depend on which of these definitions you use. Again, there were alternatives if you didn't like the way these are written. And limits at infinity, either x is greater than m if we're talking about positive infinity and m is positive, or x is less than n if we're using n as a negative number. So again, it's important to pay attention to what we're doing. But again, if I'm changing what x approaches, I'm just going to change the first part of that definition. Hopefully this helps, and I'll see you in the next video.